Okay, thanks, Mark. Thanks, Karen. Can you guys hear me all right?
Yes, we can.
Yes.
Okay, great. Good afternoon, good morning to some, and welcome to the Week 3-4 S2S seminar. Today, I'm going to talk about development of the fully coupled UFS based seasonal to subseasonal prototypes, which we have been conducting. These are right now targeted towards our next operational versions of GFS, GEFS, and SFS, which would be the replacement for the CFS V2 we have in current operations. This is a EMC-wide effort. A lot of people doing a lot of hard work. Some of the active developers of the system and running these prototypes are listed here. Can you guys see the next slide?
I'm still seeing your title slide.
Okay, hold on. Okay. Can you see my next slide now?
Yes.
Okay, great. But this is a community effort. As part of UFS, we have a lot of collaborators, contributors to the system. At NCEP, at Ezreal, at GFDL, also at UCAR, NCAR, and the NESI group. And our progress and our advancements would not be possible without active collaboration and a joint effort by all these individuals listed here. Here's a brief overview. Going to first talk a little bit about the motivation, then go into the current UFS-based coupled systems which are under development. Then specifically talk about the coupled UFS S2S configuration. Then show some results from our prototypes and summarize them, and end by talking about our near-term future plans. So as a background, Weather Service issues global forecasts at roughly two time scales. Weather, where I would put both GFS and GEFS, and seasonal from CFS. The Weather Act from Congress a couple of years ago instructed the Weather Service to provide forecast guidance extending from weather to subseasonal to seasonal scales. It so happens that the Weather Service is in the process of upgrading its operational modeling suite. We adopted a new atmospheric dicore, namely FE3. And as such, we are using this opportunity to upgrade our systems and unify our modeling capability across all these different timescales. So as a strategy, we are trying to simplify our modeling suite. The production suite, the way it is in operations today, is somewhat similar to the figure on the left, where we have a quilt of models and their products, which have come by as part of implementing solutions rather than addressing the overall requirements. But we are for sure moving towards a production suite which looks like the figure on the right, which is more of a product-based system that satisfies all the requirements and covers all the current elements of the production suite in a much more systematic and efficient manner. So this is where UFS, or Unified Forecast System, comes into play. Currently, the UFS system, the coupled UFS, consists of the following components. All of these are community components, meaning that each component is supported by folks outside of the Weather Service. So we're using NEMS, or NOAA's environmental modeling system, for our infrastructure. You will hear more about this in the next talk from Arun. We adopted CMEPS, the Community Modeling Earth Prediction System Mediator. This is a joint effort between NOAA and NCAR. As I said, we are using FE3 Dicore, and we are using that with a CCPP physics driver. CCPP here stands for Common Community Physics Package. We have two ocean models. MOM6 is the ocean model for S2S scales. ICOM is our ocean model for weather scales. The long-term plan is to unify everything around MOM6 in UFS-based applications. WAVEWATCH III is our wave model. We have recently moved to CICE6 from CICE5 as our ICE model. And we are moving towards adopting NOAA MP as a land system model component, and actively bringing in GoCart for aerosols. So each component here is a community component and has its own authoritative repository. And using our infrastructure around NEMS, it allows us to connect different versions or different instantiations of these different components to come up with coupled model configurations. More details on the link shown below. So we have a number of coupled applications under development here in the Weather Service at EMC. Some of them are listed here. Today, for this talk, I'm going to primarily focus on the one listed at the bottom right, which is the FE3 GFS MOM6 CICE6 WAVEWATCH III coupled system. This is targeted for S2S scales. The 25-kilometer atmospheric resolution, quarter degree ocean and sea ice on the same grid, and half degree waves. So as an overview of different components for atmosphere, we're using FE3 Dicore. We're primarily using GFS physics with GFDL microphysics, using CCPP for physics, and 25-kilometer C384 configuration of FE3, and we've recently moved to 127 levels. For ocean, it's a MOM6 quarter degree tripolar grid with 75 hybrid levels. The setup is very similar to OM4 as described by Alistair Croft et al. In 2019. For waves, it's WAVEWATCH III on a half degree regular lat-long grid using ST4 physics described by Arduin in 2010. For sea ice, it's a CICE6 Los Alamos sea ice model. It's using the same grid as oceans with 5 sea ice thickness categories. We're using NEMS infrastructure with a NEMS driver and caps, and CMEPS mediator for coupling between the different components. So here is a schematic, a rough schematic of how the different components are connected and coupled. So we have coupling via the CMEPS mediator for atmosphere, ocean, and ice. Waves are directly connected using what we call NEMS connectors, still using NEMS caps with atmosphere, oceans, and ice. The atmosphere ice fluxes are computed by the ice model and passed via the mediator to FE3. Ocean fluxes are computed by the atmospheric model. Wave model sends reference length information to the atmosphere and also sends Stokes drift information to ocean to describe sea state dependent Langmuir mixing. So we have conducted a series of prototypes. We have completed 6 separate series. The configurations for each one of them are summarized here in the table, starting with prototype 1, where we use initial conditions from CFSR and CICE5 and NEMS. And as we have progressed through these prototypes, we've either improved upon initial conditions and added more components. So waves came in prototype 4. We brought in CMAPs in prototype 5, along with CICE 6, replacing CICE 5. And with prototype 6, we introduced fractional grids. So all through these, our physics settings have been mostly unchanged. But with UFS prototype 6, we did change because we moved to 127 levels. 1 through 5 were with 64 levels. But elaborate physics tuning still remains to be done, as we are still in the engineering phase of our development. So to further summarize our progression here, prototype 1 was our first prototype using CFSR initial conditions. For prototype 2, we updated our ocean conditions, got 3D FAR-based conditions from CPC, also introduced slow-fast coupling time steps in the couple system. The prototype 3, 3.1, we got better or updated CICE initial conditions from CPC, introduced river runoff, and fluxes or the treatment of fluxes are separated between the ice and the ocean. Prototype 4, we brought in CCPP physics driver and introduced wave coupling. Prototype 5 brought in CMAPs as our mediator, replacing the legacy NEMS mediator, CICE 6 CICE model, and also had some updates for wave atmosphere coupling. And then with prototype 6, we brought in fractional grid to better or more accurately calculate our fluxes near the coastlines, moved to 127 levels in the atmosphere, and updated our physics in the process. More about these recent updates to physics. With the prototype 6, this is bringing in physics from the recent GFS version 16, which was made operational in March of this year. So with the increase of the vertical resolution, we replaced the KEDMF PBL scheme with a scale-aware TKE EDMF, with the background diffusivity being revised based on a stability-dependent function. Gravity wave drag was changed, and now it's parameterized for subgrid scale, non-stationary gravity wave drag. For radiation, we updated how we are treating water clouds, so radiation absorption by water clouds. And the assumptions for cloud overlap or representation of clouds in the radiation scheme was updated. For microphysics, we updated the GFDL scheme by having a more accurate way of computing ice cloud reflective radius. And for the land surface model, we are still with NOAA for prototype 6. Ground heat flux calculations were added for snow-covered surfaces. And we introduced consideration of vegetation impact on surface energy budget over urban areas. Next, I would like to present some results. So before I do that, the test plan for all these prototype runs has been the one and the same. We are testing it at subseasonal scales. So we initialize the couple system on the 1st and 15th of each month and conduct 35-day forecasts. The time period we have chosen goes from 2011-12 to 2017-18, so it's over a 7-year period. All the model components are being initialized separately. This time period covers important El Nino La Nina events, as well as years of very low ice. And 7-year period has been enough to give us a large enough sample to compute some statistically relevant metrics and assess our progress. So the overall strategy here is to conduct discrete prototypes with fixed benchmark settings and metrics. And then we evaluate these prototype results, looking for spatially and temporally persistent patterns of scale, scores, and biases. So when we moved from prototype 1 to prototype 2 and brought in improved ocean initial conditions from CPC, we of course saw an immediate impact on improvement of our anomaly correlation scores for SST. This graphic here shows the results for Nino 3.4 region. Gray is our operational CFS, V2. Prototype 1 is in pink, and prototype 2 is in green. As you can see, with prototype 2, we improved on the anomaly correlations and scores for NINIO 3.4 for all lead times. Similarly, when we moved from prototype 2 to prototype 3.1, and brought in better initial conditions for CICE, we saw improvements. Prior to that, with CFS V2 and prototype 1 and 2, ICE tended to grow too fast, and then we would lose it quite quickly. With 3.1, we saw an improvement shown in the graphic for the Arctic region in the top left. And when we look at the threat scores for Arctic ice concentration, defined as those areas where CICE covers more than 15% of the grid cell, we see that the advantages we gained with these better initial CICE conditions is maintained through our prototypes. So we got similar results for 3.1, 4, 5, as shown in the figure for threat scores on the right. Some biases have persisted. So here, comparing results for the SST bias computed using Ostia analysis for the tropics. And we find that as compared to our prior prototypes, bias has maintained itself and continues to grow over time. So this is one area which we hope to focus on as part of our physics tuning. On some others, there is some improvement. So this is looking at the OLR bias as compared to high resolution infrared sounder data. It's consistently positive along the ITCC, but when we compare prototype 6, say on the far right with our prior prototypes, especially prototype 1, we see distinct improvement. Here we are looking at the anomaly correlation scores for precipitation for weeks, for precipitation, and tropical SST and CONUS T2M. And as expected, we find that the correlations go down with lead time, and results though are similar to what we saw with the previous prototypes. So here's summarizing the AC skills for prototypes. All our prototypes are comparing with CFS. We find that when we improve initial conditions, we get a boost of skill scores as expected. The skill scores for some of our other metrics like Z for the Z500, which is the 500 millibar anomaly correlations, and CONUS T2M have remained in the same range. The CONUS precipitation skills remains low, though there is some improvement, but still overall low. But pretty much the story is that all our AC skill scores are quite similar across the different prototypes. Also, since we're talking subseasonal, we pay special attention to MJO. So to assess our MJO scale, methodology is as laid down by Wheeler and Hinden and Lin et al. In 2008, defining RMM1 and RMM2 indices. The code we are using here has come to us from CPC, and developed by Ming Hui Chen. Observations, we are using our daily OLR from CPC archives, and zonal range at 850 and 200 millibar from CDAS2 for the same time period. So here are the MJO indices for prototypes 4, 5, and 6. So for RMM1, with 6, maybe we fell behind a little bit, but with RMM2, it was better. Overall, if we look at ACU of 0.5, there is very little difference between the three. Also looking at MJO amplitude and phase errors. So in general, we have a positive amplitude bias in all prototypes. It tends to be smaller bias for stronger MJO cases, as shown in the panels in the middle. For MJO bias, which we are on the slow side in the phase, and it starts early or starts earlier in stronger MJO cases, as shown by the panels in the bottom. So the overall summary so far from our prototypes is that when we upgraded our initial conditions for ocean and sea ice, we saw a distinct improvement in our forecast skill, especially for ocean and sea ice metrics respectively. And that benefit of improved initial conditions has persisted in our subsequent prototypes. Most global and CONUS skill scores for weeks 3 and 4 especially, and even for weeks 1 and 2 are consistently above those of operational CFS. Overall, the spatial and temporal structure of the climatology of biases and scales is very similar across our recent prototypes. And this gives us confidence that the system is fairly robust and is behaving right from an engineering standpoint. Of course, we still have a lot of work ahead in reducing our systematic biases, like the tropical SST, and improving upon our skills. And we hope to do that with better initial conditions coming to us from DA for the various components, and also improving upon our physics and tuning the physics for each component, which is the plan for our future prototypes. So for our next prototype, so prototype 6 has been completed. Actually, we are still analyzing the results. So this was with 127 levels, and we adopted GFS V16 physics using CCPP and fractal grid. For our next 2 prototypes, which are planned for this fiscal year, we're bringing in NOAA MP as a land surface model component in lieu of NOAA. Looking at adding GoCart for aerosols. We're planning some major physics upgrades for radiation, for gravity wave drag, bringing in Thomson microphysics, Mehra to aerosol data for aerosols, and also updating our vegetation type using Beer's data. Some other physics, minor physics updates are also planned for convection scheme for PBL, as well as for surface layer. And we hope to, and we have started exploring marine DA, bringing in better initial conditions for oceans and sea ice. One other plan we have is to actually conduct another prototype, which would be similar to, say, prototype 8, but at a high resolution of C768, 127L. This is targeted towards GFS version 17. So we'll be mostly interested in looking at the weather scales for this prototype. And also from an infrastructure point of view, we are working towards bringing in waves through the mediator instead of connectors, and unifying our coupling strategy across all different modeling components. That's all I had. Thank you.
Thank you. We do have one question on the discussion document I think we have time for. They ask, will WAVEWATCH 3 eventually be put on the same grid as the ocean, assuming it is not being applied to lakes?
Good question. That's a topic of discussion for us. We have to maintain our current operational capability. So for our GFS, right now we are actually using a 1/6 degree grid resolution for waves. So we will have to match that and hopefully improve upon it. And for GEFS and ensemble system for the waves, we are using half degree, and we hope to do better than that. Our final grid choice for WaveWatch would be based on how many resources we have in computation, with the constraint that we have to match or do better than the existing operational scale.
Great, thank you. Okay, I think we'll pass it over to Arun for the second talk for today.
Okay, thank you. Two questions. First, can you hear me? And second, do you see a window that says UFS infrastructure?
Yes and yes.
Okay, good. So I didn't mess this up. So thank you and good afternoon. And so this is, I guess, part two of this today's webinar series, where I'm just going to give you a little bit of what we're doing for building the community modeling paradigm. This is kind of, there's a lot of people that are involved in the UFS infrastructure, so naming everybody is going to be really hard, but I'm just going to go through what I can right now. So just a little bit about what UFS is. You've already heard a little bit about it from Avichal. He's talking about it, about the UFS from the development from a couple modeling standpoint for the sub-seasonal to seasonal, as well as weather scales. So the UFS broadly is a community-based coupled comprehensive Earth modeling system, which has been targeted to improve NOAA's modeling suites. We're moving away from a paradigm of closed development to more open development. So with that in mind, UFS as such is hosted on GitHub and follows an open development path plan. The UFS can be configured into multiple global, coupled, and regional applications. Examples are medium range weather, short range weather, hurricane, etc. We already saw a talk about medium range to the seasonal scale examples of applications, and there are two others that are currently ongoing in development. Also, NOAA and NCAR have an MOA to advance a user-friendly community infrastructure that is using UFS, NCAR, and other modeling systems. So that kind of gives you a broad overview of what UFS is. So why are we doing all this? You know, our aim is to essentially reduce the number of independent modeling systems across our community. So maintain the diversity, but at the same time remove systems that are doing more or less the same thing and hopefully improve our efficiency. We want to move to state-of-the-art coupled modeling systems across our entire enterprise. We want to share common infrastructure across organizations as far as possible. Sometimes that is not possible, and then we understand that. But where we can, we want to leverage each other's capabilities and skill sets. And as well, we want to provide easy access and entry points for end-to-end systems to engage the community in model development, and with a long-term goal so that we can accelerate innovation. We're not doing this because we just want to do it. We know that the more we train the community, the better our systems will get. So we see there is a selfish goal here. The UFS itself is on GitHub, and you can go to UFS Community. There's a wiki page that kind of talks about what all is there. And essentially, if you come to the UFS Community, you'll see a series of repositories. Each repository is organized as an umbrella repository. So it's made up of individual smaller components that have their own authoritative repositories in different places. So it kind of gives you an overarching umbrella built picture. There are several institutions that are involved in UFS development and its infrastructure. There are government laboratories like EMC, AOML, GFDL, GSL. There are non-government institutions, NCAR, JCSDA, NESI, etc. There's the academia. There's GMU, OU, CU. There are cooperative institutes, more private companies, and the list is growing every day. So if you're not here and you're working on it, please don't get offended, as this is just the list that I came up with while I was getting this talk prepared. It's a growing consortium, and we are excited with that. Applications and models. So we kind of make a separation between an application and a model. A numerical model is an umbrella repository for an Earth system model that connect together to provide forecasts. That's the code base. That's what we call a model, right? So for example, for GFS V16, we've got the FE3 with physics and WAVEWATCH 3 coupled together to make one app code, which is the model. Now an application, a specific configuration, so GFS would be an application. It takes the model and it adds data simulation, there's a pre-processing, post-processing, workflow, and all the other elements that are made up of it. So here is a picture that this is always changing. So this is, again, it's a little dated picture. It's just an example of all the different applications we've got. Medium range weather, we refer to that as the GFS, GEFS. These are all medium range weather applications. And as of right now, the medium range weather application, at least right now, is atmosphere, land, and wave. But for GEFS, it's already got aerosol in it. And the subseasonal to seasonal has got waves as well in it. So this list needs to be updated. So it's always out of space, this thing. So we've got all of these different applications. Now, the UFS Weather Model is our core model that we are using. When we started doing this work, we had a UFS Weather Model which was serving the medium range weather, and we had a subseasonal to seasonal application, and there was a subseasonal to seasonal model. As we started building this out, we noticed that the UFS Weather Model and the subseasonal to seasonal model were becoming closer and closer. So we merged that into a single repository. So as it right now stands, the overarching model is the UFS Weather Model. It consists of the UFS driver. It connects to multiple components. There's a coupler in the middle. It connects to an atmospheric driver that connects to the core and physics CCPP. There's a wave component. We have now recently added data models that allow us to choose data components as a driver. Ocean, as Avichal alluded to, there are two ocean flavors, MOM6 and HICOM. MOM6 has been targeted for subseasonal to seasonal, whereas HICOM is being looked more at weather scales, primarily for the hurricane applications at this particular moment. And the long-term goal is to have everything run by MOM6. We've got the ICE model at size 6. And recently, or this is ongoing, we're adding chemistry modules, that's GO-KART and CMAC, that will be connecting with the atmospheric component. The bigger picture, a separate project, is ongoing to connect the UFS Weather Model from the driver through the JEDI infrastructure for data simulation. So it's an ongoing, all the while, development activity that happens very frequently. The applications that the UFS Weather Model is supporting. So initially when we started, these are all our different applications: the medium range weather, the short range weather, the S2S, which is our subseasonal to seasonal. The subseasonal part and the medium range weather are slowly getting to merge together as one application, where we probably have seasonal off on the separate side. There's the hurricane application, and then we've got the data simulation for the atmosphere as well as marine data simulation. Now, the UFS model itself, weather model, because the UFS is made up of a lot of components that can be put together in different ways. Initially, these applications had the UFS component models put separately, but over time in the last year, the UFS weather model has become a single entity that is supporting all these different applications. So we have one common code base that supports about the 4 or 5 or 6 applications right now. Now there are a few other applications that have got their own flavors of the UFS model there, but when they get integrated into the UFS weather model, they'll also be supported through here. Why we are doing this? It just becomes easier for regression testing, having a common infrastructure, and for overarching, making sure that the systems that support the short range weather do not break the medium range weather. The UFS Weather Model Code Repository is shown over here. You can go there to take a look at it. There is the wiki page. It uses the CMake build system for the umbrella model and underlying components. We're trying to convert everything to CMake. Right now, WAVEWATCH 3 is the only exception. We have a plan to move to create a CMake build system for WAVEWATCH 3 as well. CMake is an excellent modern build system. It comes, you can have parallel builds. It's very fast. It's easily portable. So we really like it. The UFS weather model has already been stated, can be run in multiple configurations. We can have an atmosphere-only mode. You can have a fully coupled mode. You can do an ocean-only mode where we can run a data model to drive the atmosphere and run a ocean mode. We've been using that primarily for data simulation, ocean DS activities. We have a regional mode for what we call the mesoscale applications. Right now, we're building the rapid refresh forecast system out of it. There's the hurricane mode, which is currently in development, referred to as HAFS at this particular moment. The UFS weather model serves NWS operations. We've already transitioned to operation GFS v15, GFS v16, and GEFS v12. They were all derived from the UFS weather model code base, so it's already going into operations. And we are actually developing GFS version 17, HAFS version 1, RRFS version 1, and seasonal version 1 at this particular moment. So this one code base is serving all of these activities. So as you can understand, the activity, the development platform is very active. Right now, there are 125 forks for the weather model. There are 341 PRs to develop as of today. 18 are right now open. 323 have been closed. A PR is a pull request. It essentially means that these many developments have gone in. There are 280 issues. 61 are open. 219 have been closed. We do all our interactions in the UFS weather model through the issues page. We really do not like to use emails to people because we don't keep a record of it. So everybody who wants to interact, who's having problems, needs something, should come through the issues page that allows all the code managers to review it. So we prefer that as our interaction. The code managers across multiple institutes provide a supporting role. Code managers are critical to this process. And there are, as you saw for the UFS weather model, it's made up of many different components, and the authoritative repositories for these components are not all at EMC or even at NWS. They are spread out across, and we do that. So how do we do this interaction, this dance? It's a pretty complex dance. There are bi-weekly meetings of UFS and component model code repository code managers, where basically people review and say these are the expected activities that are happening in the next few weeks, and we can kind of sync up that way. Apart from that, the core code managers that make up the code management team, the UFS weather model, have daily tag ups. They review, streamline the PRs, decide which ones, who's working on which one, and kind of leave it at that. Those are just 15-minute tag ups that are, handling immediate issues at the time. Slack remains our channel of communication. Apart from that, communication happens through the issues that are open on GitHub. The UFS weather model has an enhanced regression test suite. It's a shell-based test suite system. They run reproducibility tests, feature tests, multiple resolution tests. They look at C96, C384, C768 resolutions. We have multiple configurations. We have a regional configuration, an atmosphere only, a fully coupled configuration. And as more and more capabilities come on, we add more and more tests to make sure. The aim here is that, and this is again has been the core as to why we unified around the UFS weather model, is that when updates are provided for a particular component, we want to make sure that all the applications that are served by UFS weather model, none of them break. We also run the tests on multiple HPC platforms. We have a whole suite of what we call tier 1 platforms that this tests run on. That's Cheyenne, all the NOAA RDHPCS platforms, our operational systems. Apart from that, and Orion. Apart from that, we also run a CI/CD infrastructure that runs on AWS using GitHub Actions and containers. And that runs a much lower resolution model because we cannot afford to run the full resolution on AWS cost-wise. So all our developer interactions are managed through GitHub Issues. Here's just an example of screenshot. This is from a long time ago. Right now, we've actually gone from 18 labels to 31 labels, so that people, the code managers can assign new issue is open, then a label is assigned to it based on what its immediate need is, and then we go and process through it and try to keep an active management of this one. We use ZenHub to manage our issues. It's a good project management tool. So if you have the time, you can please go ahead and browse through the GitHub issues and all the GitHub things for the UFS Weather Model. There's an active wiki for the developers. You can go there and it provides you an idea about how you can download the code, compile the model, build it, run regression tests, run unit tests. It's always developing, and I'm going to harp on it. This is very active development, so documentation, sometimes we try to keep up with it, but it's hard. And sometimes documentation doesn't stick with what's happening at the top of development. So that's always a challenge for us. There is a guide, and there's a user's guide which we have to read the docs. Again, the first iteration of this guide was done with the first release of the UFS medium range weather application, and right after that, the problem again with all of this is just keeping this up to date with the latest developments is always a challenge and hard. Some statistics on the UFS Weather Model GitHub. It kind of gives you an idea of what's happening, what's the current status. This gives you how many people are cloning and the number of visitors that we've got. So it's a very healthy representation of the number of visits and the number of activity that's going on. We have this again an example of the number of views per 2-week period. It's just been over a period of time, these have been growing slowly, and we're excited about that. Public releases, the aim of the public release. We've had a number of public releases. Again, the aim of the public release is to introduce the community to stable UFS configurations, so as to get them more involved in the process. The public releases come with a graduate student test, and this is a measure about how easily a person can get, build, change, and test code for correctness, get documentation and user support. The public release gives us a good, a good marker where documentation is kept made up to date, and testing is done on multiple platforms to make sure things are working correctly. The public release is not the latest version of the model. To get the latest model to be on top of everything, you need to go to the top of development. But a public release is a good way to get used to the system. There are, we've had public releases tested on multiple HPC platforms. They include Linux and Mac OS platforms. We also have tested them on AWS. We've had multi-agency release teams working on different aspects of a release package. And so far, we've had 2 major and 1 minor release of the UFS Weather Model. The medium range weather application was essentially the first time we released it. It consisted of the UFS Weather Model that was in atmosphere-only configuration. We had 2 physics configurations when this was released. One was the GFS V15 physics, and another was what we call a test or a beta GFS V16 physics at that time when the release came out. And this was done at 64 vertical levels and 4 resolutions. It had a user-friendly workflow, which was SEAM, and had pre and post-processing tools. It came with a unified build for the libraries, which was critical because it allowed you to build all the libraries that the model depends upon in a consistent manner. And that was very important to be able to port to different platforms. Since then, we've had a minor release that had essentially updated CCPP dependencies to Python 3 for the physics packages, and has had bug fixes for pre-processing tool sets and ability to ingest GFS with 16 net CDF initial conclusions. These are some minor updates that have happened. Since this release has happened, we've gotten an operational implementation of GFS v16, so that physics has been finalized, and it's actually at 127 levels. So that release is not available. I mean, it's available in the sense that it's available on GitHub. You can check it out, but we haven't done a formal release, operational release of that code. For the public release for medium range weather app, we had 3 levels of platforms that we used. We had a pre-configured platform, which was level 1. In this case, in these level 1 platforms, all the model libraries were already installed and the workflow model was built and run out of the box. We did comprehensive testing before the release. This level 1 platform are all the NOAA R&D platforms. We did this on Cheyenne and Orion as well. And we didn't do it with WCOS because that was already being tested and built at that time. Then we defined what were level 2 or configurable platforms. Here we did not provided the libraries, but we tested and built it and made sure that the libraries worked. Example of this is essentially Stampede, and then we did some comprehensive testing. For level 3 platform, we just did a few limited tests where we expect the model to install and to run, but we didn't do enough testing. These are your generic Mac OS or Linux clusters that people can test with. So that was our medium range weather, and then the physics suite that we provided for medium range weather were 2, as we explained. There was a V16 beta and the V15 physics, and the main difference between the beta and the 15 physics was essentially the PVL schemes that was used. Then we've also had a major short range weather application release. This is a limited area model capability of the UFS weather model. Again, it's the same CMake build system. The application comes with pre-processing, model execution, post-processing, some Python scripts of basic graphics. The workflow that is used for the short-range weather applications is different from the medium-range weather applications. So that's one area of unification that we are looking at, is how we can have a comprehensive workflow that goes across our application suites. That's work still to be done. And there's a lot of documentation, and there's the user support forum for it. And again, for the short-range weather application, we had 2 configurations of physics suites, GFS V15 physics, and what we're referring to as the RRFS version 1 alpha physics suite. It's just in the beginning stages of development. And so, again, details about how the 2 suites are different are given on the slide here. So that is generally, apart from just about the UFS weather model, we have a forums page. You can get to the forums from the wikis of the UFS weather model or from the UFS weather application. The forums are hosted. The forums are there to provide discussions and question and answer sessions, and there is support for it. So if people have issues, they can either come to GitHub Issues page or go to the forums to see if there are other people who had issues and discussions and stuff like that. Take-home message. If with all of this, if I could provide a few take-home messages, one that I want to talk about is that code development in an open environment requires it has advantages. We think it's the future, but it does require some things that people have to take into account. Ownership. We're all in this together. It's not somebody else's thing to solve the problem. We all need to take ownership about what can and cannot be done. We all own this thing together. We need to have mutual respect for each other. People have ways of doing business. They like to do their, they have a certain way. I have a certain way that I like to code, and somebody else might have another way to code. And we need to have respect for each other. Otherwise, this will not work. Communication. is critical. People need to know what people are doing, and sometimes not communicating well can lead to more fractions and more issues than needs to be. And one thing that I put separately from communication is that a lot of people think communication is one way, is that you're talking and everybody else has to listen. A more critical aspect of communication is listening, and listening is key. Patience is key. The key, when you have code that is very actively being developed, you'll have sometimes things will not work straight away off the bat for you. You need to be involved in this. You need to have patience to make things happen. There are people who are working very hard all the time, and we need to respect that. Adherence to rules of development. The rules of development are built by the community. They're not thrown from top down, and they're built by the code managers. Come up with these rules, but we think of them as a democratic process. These rules are built so that codes can be worked on seamlessly and together. And it's critical when you're working on something to keep up to date. I cannot thank the code managers enough. All of you, I hope there are a few here, all of you have made this happen. Without you, we would not be successful. And it is absolutely critical to get good code managers and integrators into this. And the more they are, the more support we can give them, the better the whole system will be. And finally, good documentation is an integral part of development. We like to develop our models, but we never like to document. Documentation needs to become an inherent activity for us, otherwise open development just won't work. So it's absolutely critical we internalize it. Like we would internalize writing publications. It is critical that documentation become an integral part of development. So with that, I'm just going to end with a little bit of a show and tell, which kind of gives you an idea about how much and how fast this model has been developing. This is just a little graph about how the UFS Weather Model has developed. The repository is developed as a function of time, as things have been added on to it. It's an actively developing repository, and people work on it all the time. So with that, I'm just going to stop here and take questions, if any, from people.
Thank you. I do not see any questions on the discussion document at this time for you. We can give it another minute or two.
That's good. So everybody is aware of how things are working in the UFS Weather Model, and nobody has any questions. That's perfect.
Aaron, I have a question.
Yes. Sure.
Yeah. The question is from the point of the new users who has run other models. They want to try this model. Do you think they can do that just by looking at the wiki page, then learn how to download and build and run the model?
So there was a for first-time users, the easiest way is to look at one of the releases, because we know that the releases were well packaged and tested, and that's the easiest thing to test and get familiar with it. After you've done that, then you can go to the top of the develop and then try to build and run the system. We are always, we would love for people to go to the top of develop and start running and testing, but our documentation is always a little behind the top of develop, and we're always struggling to catch it. But the releases are well documented. So if you go to any of the release from the wiki page, you can go to the particular release and there is documentation supporting that release. You can use that to build and run the system. And once you've done that, and once you want to develop and become part of the development, you can go to the wiki page. You can try to build the system and then go to the issues and put questions there if you're running the issues. And then there's the forum.
Yeah, the focus here probably are interested in running the couple system, the prototype model, which is not in the public release yet. What was the timeline for the public release of the couple system?
I think that one with Epic coming on board, I think that's a discussion that will happen at the Epic level. There are two sides to it for a public release. Is from the scientist side, they feel that yes, the couple model has reached the level of development that they feel comfortable. And from an engineering perspective, once the scientists feel comfortable with this level of development, we need to make sure all the documentation is in place, and then then the testing that has to happen on multiple platforms for release. That's, I think, is going to be probably one of the activities that have to be discussed with the new Epic project. The Epic.
Sorry.
Does that help?
Oh, yes, thank you. I would encourage folks to contact Avichal and Aaron if you are interested in either looking at the data has been run from the prototype runs, or you are interested in start to look at the code. We need a community